meters. At an angle of 30, okay, to the horizontal, the box is pulled up by means of a lightning eccentric string held parallel to the, okay, force applied is 700, good. What is the name given to the force in a rope? So all ropes, all strings, they usually possess one force, and that is the tension force. So the force there is tension. Please don't tell us force applied. It's the tension force. Okay. Then 5.2, give a reason why the mechanical energy of the system will not be conserved as the box is pulled up the plane. So the reason for this, okay, why energy is not going to be conserved, because the surface is rough. I mean, as you're trying to pull it up, friction is trying to pull the box downwards. So in that way, you'll have to cover up for the losses and all of that. So we can say that the presence of friction, the presence of the frictional force, we can also say the tension in the system. Both tension and frictional force will have an effect on that. Okay, then the box is pulled over a distance of 4 meters. So from here up to there is 4 meters. And then the kinetic frictional force between that is 178.22. They want us to draw a free body diagram as the box, or for the box as it moves up the incline. Okay, so with this, before I even draw the free body, just look at the forces that are going to be acting on the box, the way it is. So we know that this is going to be the force applied. Whenever we have an incline, it's automatically that the FG parallel will always act downwards. Okay, remember we said we don't want components, but I might be forced to put it. So frictional force is also going to act downwards. And then we're going to have the weight and then the normal force, the N up. How many marks is it? It's 4 marks. So if we can have just 4 forces, that will be good. Okay, so we're saying force applied, and this force applied is in the form of the tension. Okay, and then we can also have the frictional force, which is F. And then we say the normal force, and then we can have our weight, which is also okay. Alternatively, you could have the normal force, the tension, even this component, FG parallel, because it's acting downwards anyway. Okay, because our focus is just going to be the motion along the incline. So you could also indicate it the FG parallel. Okay, so that is the free body diagram. These two have to be in a straight line. I don't know why mine is Q. I know it's a weekend, but good. Okay. Then 5.4, they want us to calculate the work done on the box by the frictional force over the 4 meter. So from our formula page, we know that the formula for work done do we have it here? It should be here. So this formula here is what I'm going to use. Okay. So we're going to have W, work done by the frictional force. I'll just call it WF, is equal to F multiplied by the delta X and then the cos of theta. So my frictional force is 178.22 multiplied by the displacement, which is 4 meters. And then I'm going to use the cos of 180. Why are we using 180? We know that the object is moving up the incline. Okay. So up the incline will be our reference point, which is a 0. But then frictional force is acting on the opposite, which means it's acting within an angle of 180 in the opposite direction. Okay. That's why I'm using cos 180. So I punch that into my calculator. That's going to be 178.22 times 4 the cos of, we said 180. That's correct. So that's going to give us negative 712. Okay, comma 88. Remember, this is work done. Work done is measured in joules. So the explanation for the negative sign is just the direction. It's acting in the opposite direction. All right, then 5.5, use the energy principle to calculate the speed of the box after it has moved 4 meters up. I need space, I need space. Okay, let's just explain this nicely. So one thing we know about energy principles, remember we said we have WNC is equal to the change in EK plus the change in EP. But we also say that the net work done should be equal to the change in the kinetic energy. Okay? So I think I can use this one for me. The net work done should be equal to the change in kinetic. So in that way, I'll have velocity involved straight away. So let me just scratch this out because I need space like badly. All right, so for the network, since the direction is up and there's just one force that is working up there, so I'll look at the, let me not use that. We're saying net is going to be the work done by the tension, okay, plus the work done by the frictional force, and then the work done by the FG parallel, because from our free body, we saw that FG parallel and F frictional force are acting in the same direction. Okay, let me just get this first. So work done by the tension is going to be 700 multiplied by 4 multiplied by the cos of 0, since it is acting in that direction. And then the work done by the frictional force, we already got it as 712.88. Then plus the work done by the FG parallel, we know that the force FG parallel is given as the mg sine of theta. Okay, so this theta is this angle of inclination. The cos theta here has to do with just the direction of motion. Okay, so I'm gonna use this formula and say the mass is 70 times 9.8 multiplied by the sine of 30. So that's just the force. I'm multiplying it by 4 and then the cos of 0. So if I try to substitute this or punch that into my calculator, first, so 700 times 4 cos of 0, I'm getting 2.8. Okay, negative 12.88 plus 70 times 9.8 sine of 30. And then I'm multiplying by 4 cos of 0. So this is giving me 3459. 3459.12. So this is just the network. Okay, so we say network must be equal to the change in kinetic energy. So the change is going to be a half m. It's going to be v final squared minus v initial squared. I think that's how I can best put it. Okay, so I'm going to equate all this to 3459.12. We know that the mass is 70, so a half of 70 is 35. Then I'll divide both sides by 35. and then replace all the other information. So what do we want? We want the initial velocity calculate. Calculate the speed after it has moved up. So which means we need the final velocity. Initially, this thing was at rest. If I am not in forward, is at rest, perfect. So which means the initial was a 0. So which means our VF squared should be equal to this divided by 35 and then under the square root. Okay, so let me divide this by 35 because a half of 70, I'm getting 98,832. And then I need to find the square root on either sides. All right, square root is giving me 9,94 meters per second. Okay, 9,94 meters per second. So guys, that's how we would have obtained those 5 marks. I don't know if there are other options of how to get that, but this is how I'm getting mine. This is how I'm getting mine. Someone is saying, let's go back to the calculations and just confirm. Yeah, there's a problem. There is a problem. There's a problem. Okay, let me just, because I've seen my mistake. So this is going to be wrong. Same applies to that. So the wrong thing is this part. Okay, remember we said it's 70 times 9,8 sine of 30. I'm multiplying it by 4 and then the cos of 180. Why are we putting the cos of 180? Because it's also acting in the opposite direction. Thank you for that. So this is also not in. This is also out. So I'll have to redo it again. So 700 times 4, cos of 0. We said negative 712.88. Okay, plus 70 times 9,8 sine of 30 times 4, and the cos of 180. I'm getting 715. Okay. Comma 12. 715, comma 12. I'm gonna divide it by, we said, the 35. This is gonna give us 20. So VF squared is 20,432. Because remember, this is a 70, then simplify. So the square root of that, square root, I'm getting 4,52. 4,52. That is meters per second. Thank you very much. Okay, then we move on. So we have to erase this also. You say it's 4,52. Then when the box is 4 meters up the incline, the rope breaks, causing the box to slide back down the bottom of the inclined plane. What will the total work done by the frictional force when the box moves up and then down the incline to the bottom? Okay. So looking at the work done by the frictional force, remember we got it as negative this much. This was just